Right now we have seen gradient descent and we have seen how to get the weights that should be optimizing um, our cost or should be minimizing our cost. So we basically looked at the gradient descent. Okay. Okay. So let's consider some variations of the optimizers that would make us go to the global minima much faster. Again, remember, we are trying to get the weight that would minimize the cost. The gradient descent is one approach. We have other approaches, but the thing is, we need to change gradient descent a little bit such that we can go to the global minima much faster. Because with gradient descent, you would just go ahead with the steps according to the multiplication of the slope with the learning rate until the point you hopefully achieve your global minimum. Okay, so what would happen if we can somehow make this a bit faster so that we can go to the global minima like that? Okay, so people have thought about some methods. So yeah, so we can consider our whole data to be something called batch, okay? And we say that we get the whole batch if we are using our like all samples, okay? The whole data set, okay? And then we could achieve the effect of updating our weight value, but not after taking into account the whole data set, okay? So with other line, we were updating our weight values after taking the whole data set. So we were multiplying W transpose with X, okay? And then we were doing this to get Z and then 5Z. And then we compare this to Y hat and we get the slope. And then we update our weight. And we were using the whole batch. We were using the whole data set to do so. Okay. So people came up with the idea, okay, let's take what we can call many batches. Okay. So we can adopt another approach saying that this is a mini batch approach, and we can do this and say that this is mini batch gradient descent. So we'd basically be trying to update our weight with a small batch from our data. So if this is the training set that we were using here, I'm just putting it here. And instead of using the whole data set and then calculating the error and then updating the weight, and instead of doing that, I will be using a small portion of that. Okay, and this would be my batch. Okay, this is the small batch that I will be using. Okay, and after updating my weight using this port, I will be using a different port and then update the weight and so on. The effect of doing that is making this learning a little bit better, okay? Because it could make this a little bit faster if we do it this way, okay? If we take small ports, because if they are in a good way, behaving in a good way, meaning that in a way that will help us to go to the global minima, then this would make this jumps a little bit uh, bigger so that we can go to the global minimum. Okay. And we can say that this could, in some problems, be necessary actually, because in some training sets, they are just so huge. Like, let's say that we have million samples and we have many features. It could be impossible to fit this whole data set inside of the memory, okay, of the machine, so that we have to update our weight by just splitting the data into smaller parts like that, and then updating our weight with every batch. Okay. Okay. So any questions on this part?
Yeah.
Okay. So let's now consider the 2D version of that. And now we have mentioned our first variation of gradient descent. So we had gradient descent, now many batch gradient descent, and let's consider even more and more optimizers that will help us go to the global minima much faster. Okay, so if we have one weight, let's say one bias, looking like that, and we imagine that this is our, of course, global minima, then we could say that our steps could be looking like this. So we might start from here and we take different jumps like that are getting smaller and smaller because the slope is getting smaller until we reach the global minima and we reach convergence. Okay, so we say that our classifier is converging. Okay, it reaches this this point. Okay. Okay, so let's introduce a concept that would really help us understand what is coming next. So we need to now see a variation of the gradient descent, which is gradient descent with momentum. Okay. And by the way, we can name this stochastic. So we can say that this is a stochastic gradient descent. Okay. It's referring to the same thing. Okay. When we take small parts of our data, actually stochastic algorithms is when we are doing this in real time. So we're just feeding our model with one sample at a time because that's real time. And we call this a stochastic. Okay. Okay, so let's introduce a concept and see how it really could help us optimize this effect. Okay, so let's extract this part. Let's extract this part from our optimizer. Okay, and let's just think about it. What will happen if we try to make these two arrows? I'm just redrawing them, these two arrows inside of this part. Okay, what will happen if we almost try to get this end and just grab it in this direction and this end grab it in this direction, such that we make the same arrows just go like that. Do you see what I'm trying to say? I'm just trying to smooth this effect because there are a lot of variance and there are a lot of variations going up and down. There are many fluctuations in this behavior, right? So if we try to make this a little bit smoother in the direction, I will take the same arrow, just rotated like here, okay? And rotate this one in the other direction. So in that direction, okay? We will make this smoother and surprisingly, we will be going faster to the direction of the global minimum, right? So
Mm.
if we can smooth this variation that we see here, we can establish this effect and just go to the global minima faster, okay? So let's have an algorithm that will help us in doing that. It's called, this method is called exponentially weighted averages. Okay. Okay, so let's see what is the meaning of that, and then we can look at how this could help us understand our new optimizer. Okay, so let's say that our data is variable. So we have our samples, we have some samples looking like that, looking like that, okay? And we are just trying to see the behavior of these samples. So we would know that if I'm plotting the relationship between each point and the other point, it will be like that. So there are many variations. If I just consider every sample without considering any other variable. Okay. Okay. Exponentially weighted averages said that simply do not just consider the value of this variable. Okay. Consider the value of this variable and the value of the previous variable. Now let's imagine what will happen if we take the average of the two. And instead of saying, let's name this x, okay? And instead of taking the value of x, I will be taking the average of x and this value y. So what do you think will be the new x value? So now x is not x itself, it's the average of x and y. Where would be the position of x?
Same line. In the middle.
Okay, so it will be in the middle, right? Yes, exactly. So right now, this would be in the middle. Okay, that's our new x. So let's put a curve describing this. Let's put it with a different color. Okay, so if I take the average, here it will be in the middle. And y, if it's the average of y and the previous y, okay, it will be in the middle, right?
Yeah.
So all of that will be in the middle. Do you see what is happening? This variation is getting very smooth, right? If I consider the previous point, correct? If I just consider the previous point, then I would have a smoother version of my variable signal, right?
Yeah.
Okay, perfect. So here in this example, I said that x would equal x plus y over 2. I was just taking the average. Okay, so this is like taking a weight of half of x, right? Plus half of y. True?
Yeah.
Okay, that's perfect. Then you have a weight. Then you have a weight for the current point. Okay, I'm just trying to derive with you the main rule here, okay? And we have a weight for the previous point, okay? And the general formula that we had before, like the one that was varying a lot, it means that the weight of the previous sample was 0. So now we're trying to go to the general form, okay? Because I was just depending on the current value, not the previous time point, okay? So that's why the weight was 0, okay? And when we increase that weight, when we increase that weight for the previous point, okay, going from 0 to half, we are achieving more and more smoothing, correct?
Mm.
Perfect. Okay, let's now consider a general form. I think now we are ready for the general form of this. So we would say that we have a variable, let's say VDW, okay? It has a weight, okay? And this weight is multiplied by VDW, which is the old time point, so T minus 1, the previous time point, plus 1 minus this weight. You see, there is like 1 minus relationship between them because here I was taking 1, then I have to take 0. Okay, so this one is always 1 minus the other one, and this was half, then this 1 minus half, so it will be half, and then 1 minus beta 1, okay, of d w. Okay, okay, so this would be our equation now, and this dw is our current time point t. Okay, I think this is really good because now we have seen the same equation because that's at the previous time point. This is like y, okay? And it's multiplied by a weight plus the current time point x, which is this one, multiplied by 1 minus that weight, okay? And then VDW is basically the new update value that we will be using, okay? So we will be using VDW to update our weights, okay? So right now we have seen what we wanted to do. We wanted to make these arrows smoother. We just grab this part and put it here and grab this part and put it there, okay? And we had this exponentially weighted averages achieving exactly that because it took those arrows and it was just making them smoother, right? Okay, so right now this VDW is initialized with zero value, okay? This is initialized with a zero value. So what I want to do is basically take this and make it unbiased because this effect is biased because when it's initialized as zero, then this would mean that I don't have a previous time point, okay? So it's basically zero, okay? So this is not really fair for the first point compared to other points. And this would make our weight update a little bit biased, okay? Actually, in practice, sometimes it's even biased, and that's fine because it doesn't really matter when we have a lot of iterations. But anyway, to smooth this effect, we take the value of VDW and we divide by this quantity. So we take 1 minus the weight that we have, beta 1, power of t, which is the time step, okay? And then we would have our VDW, the final value of the VDW, we call it unbiased, the unbiased VDW. Okay, so all of that is fine. So how about the update itself? Before we had delta W, right? So how would we use this kind of equation to update our weights? Okay, the weight update is simply will be W old, or this would be W new. So that's W new. It will be W old minus, okay, and instead of using eta and then what we used here, it was the derivative of the cost, okay, it was the slope, we will be using VDW unbiased, okay, and that's how we would update our weight, okay. So basically when you calculate the slope, you calculate the slope that's delta W that we know before. Delta W is dW. It's the same. So that's delta W, okay, of the current time point. So the current time point is multiplied by 1 minus the weight that we have, beta that we have. And by the way, this is always a high value close to 1. So that's like 0.9. Okay. So we basically take 1 minus 0.9 and we would see that 1 minus 0.9 is 0.1. So this will take a small portion of our current time point, and it will take most of our weight update from the previous VDW. And this would achieve smoothing because now I'm not depending on the current, I'm depending more on the previous. And that's how we achieve the smoothing. We achieve the smoothing by making this value higher, the weight of the previous point higher. And that's exactly why beta 1 is close to 1. Okay. VDW is initialized with zeros, so the first one will be 0. So you will be entirely dependent on the current point, and then you go into the second iteration and you have your new VDW that will be used as the old VDW for the new time point. Okay, so is there any problems with this?
No.
Okay, perfect. So what we described here, we didn't name it actually. We just said that we will be using the exponentially weighted averages to help us achieve our new optimizer, right? Our optimizer that we are describing here with these two equations is called momentum. Okay. And this is really nice because if we think about it, this is like momentum in physics because if our data is looking like this and we have a relationship between our weight and our cost looking like that, so it is not very smooth. So we could be stucking at this uh, minima, okay? With momentum, we could take bigger steps. We take larger steps into the direction of the global minimum because of this smoothing effect. So it's almost like in physics, because momentum in physics was mass multiplied by velocity. Okay, so it's almost like we are gaining more momentum by depending on our previous points and getting bigger and bigger steps towards the global minimum. Okay, we're achieving this smooth version of our steps, and that's why they are calling this momentum. And there are some equations actually seeing the analogy between this kind of equations and the equations of physics, but it's just nice to see that this is actually relating to something physical. Okay, so right now we have our equation for the update of weights. We have a similar equation for the update of our bias because we have beta 1, it's very similar. V dV, okay, plus 1 minus the weight multiplied by the previous, multiplied by the current slope. So that's the current one, the current bias, and that's the one of t minus 1. That's the one of t. Okay, and to make this unbiased, again, we just divide this by this quantity. Okay, and then basically to update our bias, we just take this bias new. It will be equal to the old bias minus the learning rate multiplied by this quantity. Okay, so now I think we can implement this easily. We're not going to do this right now, but I think the idea is clear that we are just changing small part of our data and it will be dependent on the previous and the current points. Okay. Okay, so let's look at another optimizer showing another variation. This optimizer does not depend on the momentum that we said, it depends on the second momentum. It's called RMS prop. Okay, this is the root mean square. Okay, and this optimizer depends on the second momentum. So its variation is very easy to grasp because VDW and the previous one equals beta 1, beta 1, it was multiplied by the previous time point. So for RMS prop, I will just say that this is beta 2, just to differentiate this weight from the previous weight. Okay. So this would be beta 2 multiplied VDW. And this is also for T minus 1. So if you see, I'm just typing the same equation. Okay. The difference would be here. The difference would be here that we are taking this to be squared, okay? So that's delta W squared, okay? So this would give us the second momentum, and we are again smoothing by the same quantity, but just using beta 2. Okay, okay, so right now What about the update? The update is not using VDW, okay, itself just like that from the calculation. It's using eta multiplied by 1 over the square root of VDW. Recall that the update was like that W new equals W old minus eta, and then here it could be delta W, it could be whatever, okay? And for the new update of RMS probe, we will be having the root mean square. So it's coming from the name. We're taking the root, okay, of the mean of square, okay? And that's why it's called like that. And this is how we update our weight. So just a plug in, of course, calculate the slope, plug the slope into this equation, calculate this value, then so you will have VDW, calculate VDW here, put it in this equation, calculate this term, and just put it here. And this would be your new weight. Any questions in this part?
No, no.
Okay, so VDB will be very similar. So we'll be using beta 2, VDB plus 1 minus beta 2 dB squared and 1 minus beta 2 t. Okay, that's good. So are these all the optimizers that we can think of? No, there are several ways to do our optimization. So we can actually think about gradient descent. I think that we have now seen some variations. So we have seen stochastic gradient descent, okay? And we have seen a stochastic gradient descent with momentum, and we have seen momentum, okay? And we have seen RMS probe. And now we will explain another optimizer, which is really just gathering or combining together RMS probe and momentum. And we will see Adam. So gradient descent was really the core for all of these optimizers. Okay. In the meantime, this is not the whole story because there are other optimizers like coordinate descent. That's another optimizer which is really nice because it could optimize two variables at the same time. Okay. And there is Newton method, which is another different, like a different approach of looking at this. Because with Newton, we can, and instead of using the learning rate, I'm just mentioning that this is a method, okay? I will not be asking you about coordinate descent or Newton method. It's just for you to know that there are some other optimizers out there that you can explore if you'd like, okay? So Newton method, we don't have explicitly the learning rate. We have like a derivative of our um, slope. We take the second derivative of that, okay, and we divide by this quantity. But the problem is when we do the Newton method, we need the inverse of our data. And the issue is that if we have a data set with a lot of features, we wouldn't be able to get the inverse of something like a covariance matrix of the data because we have a lot of features. This would increase the dimensions of the matrix for which we need to take the inverse. That's why if we have many features, it wouldn't be very easy to use something like the Newton method. Okay, so anyway, we were explaining these methods, and there are many other methods that we can use. So Adam is basically an adaptive momentum take on optimizers. Okay. So what Adam is really doing, which is By the way, this adaptive momentum, this ADAM is like the most popular optimizer right now that you can use. So you can just say that you are going to use ADAM optimizer for many problems, and it would give you good results, I think. So in ADAM, basically, we took the weight update to be a combination of RMS probe and momentum. So we took VDW, okay, divided by the square root of VDW. Okay, if you see here, this part dividing by the square root of VDW, that's for RMS probe. So the part here is actually from RMS probe. So we take the VDW of RMS probe, okay, and this other one, this other VDW is the VDW of momentum. Okay, so not to confuse them because they have the same symbol here. That's VDW of momentum, okay, and that's VDW of RMS prop, okay. And what Adam was doing is basically just combining them. So if you remember, in this one, we had, in the momentum, we had the weight update to be VDW, okay. So Adam took this VDW and divided it by RMS prop. And RMS prop was in here. So it basically combined them into one equation like so. Okay, so there is one small detail in this. Of course, we have eta here, okay? But there is another detail, which is what will happen if we have VDW to be 0? Because remember, we start VDW by 0, and it could be very close to 0 at some times. Okay, so we could put a very small value that we call epsilon. Okay, it's a very small value for error basically. Okay, and we can put this very small value here in this equation as well. This value could be very small value that wouldn't change the weight update. So we can put this something like this, 10 to the power of -8 or something like that. Okay, so this would prevent our calculation of the weight from being from overflowing, basically, because if you have 0 here, it will just give you nan. So instead of just overflowing with very small values could give you, when you flipped it, will give you very high values. So this could cause overflowing. So we just put this very small numerical value. Okay, so for the bias, we'd have B minus eta VDB over VDB, okay, the square root of that. Again, that's for momentum, and that's for RMS prop, and here we put our epsilon. Okay, so do you have any questions in this part?
No.
Okay, okay, perfect. So let's take a 10 minutes break and come back to that topic, okay?
Okay.
Okay, so we can also use some other methods. Remember that we said that L1 regularization is achieving some sort of a feature selection because it's basically putting some zero values for some features and keeping some other features, and that's doing some sort of feature selection. Something on the side just to know that we have different methods that can achieve this. So we have feature selection. If we want to do feature selection, just to give our classifier fewer features that are more relevant for classification. So we can use something called mutual information. Okay. And this is based on information theory. Information theory and the concept of um, information gain and the concept of entropy, Shannon entropy. If you'd like to read more in this. And we could use something like sequential feature selection. And in this, we can just give our classifier the features one by one and just see like sequentially until we see when the classifier is performing worse. Okay. We can use different methods. There are several methods. We can even use a random forest to choose or give weight to our features. Okay, so there are several methods that can help in doing this kind of feature selection. Okay, so that's just something to be aware of that L1, yes, it could achieve some sort of feature selection, but there are several different methods that can help in doing this. Okay,